Good morning. What I want to do is, honeybees are pretty unique when you look at breeding. There's worldwide, pretty much the focus now is selection breeding, which is awesome. But honeybees, they really present some kind of unique challenges, just the nature of what they do, the multiple mating, hybrid combination, those things. So I'm just going to kind of run through that quickly with you. Really, you need to look at genetic diversity. There's 28 subspecies. What I mean by that, Italian, Carniolan, Caucasian, these are just different races, subspecies of bees, worldwide. And the origin of these is Africa, Asia, pretty much. So what we've done, the US, New Zealand, Australia, we've brought a small subsampling of a few of these and created this huge industry. So genetic diversity is really important. It just gives you, it's your tools for selection. It's like a paint box. The more different paints you have in there, the more beautiful your paint's going to be. So if you look at genetic diversity in those terms, that's really what we're looking at mostly. And if you look at diversity at the population level, what diversity do you have in the gene pool? You also want to look at diversity within the colony, which is basically how many drones has that queen mated with and how related are they to her. So there's kind of two different levels of that genetic diversity. And if you look at the genetic bottlenecks over time, what's happened, you have this small population, we call that a founder effect, which is this population you're selecting from. You've got just genetic drift, just the nature of changes over time in the population. You've got a small, very specialized queen industry that they're selecting out the best stuff they want, and that does reduce the population as well. Then you've got parasites, pathogens, just taking colonies out, which on some levels, hopefully they're taking out the more susceptible ones, but that's another loss. If you look in the US, we pretty much lost our feral population, and that was contributing to the gene pool. Commercial queen producers, there would be some contribution from those drones in open mating. So those are things. And bees have a just their whole mechanism is outcrossing. If you look at the way they mate, those queens fly out, mate with that random assortment of drones in the congregating areas. They have a really high rate of recombination, which it's just the genes doing a little dance. And like when you have a mother-father, the daughters of that are different from the original parents because you have this really high rate of recombination, higher than any other animal. Any other insect even. It's pretty amazing. So their whole strategy, again, is that outcrossing, is diversity. And if you look at, you kind of think of mutations as a negative thing. This is really kind of a testing ground. If you have some new, something from the environment, a change in climate, new pest, pathogen or something, it's their ability to kind of test what works. How can I manage this in a little way? So the more diversity you have in there, there may be some rare alleles that are just kind of sitting there, but you have environmental pressure that might increase the frequency of that and bring that out and give them a little more ability to deal with whatever is going on there. The high mating frequency, we talked about this before. This is an abdomen of a drone and a queen during the mating process. So the semen is collected in the oviducts here, and it migrates up into the spermatheca. This is the spermatheca. This is a virgin, crystal clear, and once the sperm is stored, you have kind of this marbly color. So, and when the queen mates, she's mating with numerous drones. She's going to discard majority of the semen, maybe 90%. It looks really inefficient, but what's happening is the semen is mixing in here, and she takes a little bit of sperm from every drone she's mated with. It's another mechanism for maintaining diversity. If you look at that mating flight, that's high risk to go out there and mate with all these different drones. You might get eaten by a bird or a dragonfly or something. And then she discards the majority of that semen she's collected, just so she can have that diversity, a little bit from everybody. So the semen's pretty well mixed in there. It's not layered. It's pretty well mixed. Amazing organ, the spermatheca. This is a spermatheca. This is a picture done by Megan Taylor. You can see the sperm have really long tails, so it looks kind of hair-like, but these are little sperm. I'm going to show you kind of an amazing picture. This is the spermatheca, and the next shot is like a high-speed picture of the spermatheca. You can see the movement in here? So the sperm is moving all the time inside that spermatheca. It's mixing. Just another mechanism for maintaining that genetic diversity, really critical to the bees. The drone congregating areas, that's another really kind of looks like chaos, very random. You'll get colonies, like 200-300 colonies contributing to that drone pool, another mechanism for diversity. The process of sex determination, there's one gene that determines sex, and the queen has two sets of chromosomes. The drones each have one. So the more different the drone she mates with, you'll get basically it turns into high brood viability. So this is like if the queen mates with a drone that has a similar sex allele, you'll get this diploid situation where the bees will remove that larva as soon as it hatches. It's not viable. So that's again the game. More diversity of the sex alleles in your population, the higher the brood pattern, the more solid the brood pattern. Drones, of course, I can't emphasize how important these guys are. And really, if you have any stressors in the environment, or the season is late or early or something, drones are the hardest to maintain. They're expensive on the colony, but they're really essential. How well the queen mates, extreme polyandry, the many drones she mates with, the bees perceive how well mated she is. The more drones she mates with, the fuller her spermatheca, the more attractive, the better fed she is, the better cared for she is, and the better she can contribute to the colony fitness. I'm going to go through these kind of fast because of time. So patrolines, what I mean by patrolines is a group of worker bees fathered by a different drone. So the more patrolines you have in a colony, a lot of these will specialize in particular tasks. You've got an age distribution of tasks, but you also have specialists in there. Like you may have, say you're trying to select for hygienic behavior. If you put more pressure on the colony to do that, then you can increase the frequency of those traits, or you'll be selecting for those subfamilies that contribute to that behavior. So that's really important for the bees. If you do single trait selection, for example, you can select very quickly for hygienic behavior if you do single drone inseminations, but you may have a colony that cleans out the diseased brood, but it'll be so intense that no one's making a living. It may not be productive. So you really need many of those different patrolines to give that fitness. For example, what makes honey production? It's got to be lots of different traits in there. And that includes resistance to pests and diseases, so the bees have a higher level of fitness. The environment is a huge impact. You have a lot of pressure from the environment, the forage, when they bloom, what blooms, conditions, wintering, just all these different things. So it really is that environment has pretty much an equal contribution to the genetic makeup. So that combination, you want to make sure the bees are well adapted to your area and have that diversity in them to be able to do things. Epigenetics, this is really an interesting, it shows that its response to the environment will change, it will up or down regulate genes. So you may have something that's not really being expressed, but you have the environmental impact of that can upregulate something or turn that on. For example, talking about hygienic behavior, that'll upregulate the olfactory genes so that they're more responsive to that. And it's all about natural selection. It's just putting that pressure on the bees to deal with their environment, whatever's in the conditions out there changes, having a lot of different variety within your colony so they can make those changes more efficiently. Whatever that is. It can include pesticides even. So your evaluation and selection program, you really need to look at different traits. And you're selecting for behavior. Behavior is flexible, dynamic, it's constantly changing, depending on the environmental cues, depending on the genetic makeup of your colony. So you really have to kind of consider that. You need a reliable method to measure that. Like, for example, if you're doing honey production, you have a row of colonies. This one on the end is the best producer. Is that because of the way you're getting a lot of drift into that one colony, so you get a lot of foragers there and it looks more productive? Or is it actually that colony has a higher propensity for nectar collection, things like that? So you really have to kind of look at the environment, the behavior, and make sure that you're selecting based on more genetic traits. Let's see. This is kind of interesting. If you look at the loss of in one generation, if you have your select breeder queen and you just randomly mate them out there, you'll lose half of that complement, or half of that genetic makeup in one generation. So this can go down really, really fast. It can also build up really fast if you have controlled mating, if you have isolated mating and you can maintain those. That helps a lot. If you're doing isolated mating, you want to do that within about 7 to 11 kilometers. About 11 kilometers, if you put drone sources and queen sources apart, they have a harder time finding each other. So that's a fair distance. Drone saturation, usually 1 or 2 kilometers and you want to surround that on every direction because those drones are coming from lots of different places. Again, instrumental insemination is a key. It takes a little bit of practice, expertise, equipment to do, but it's a really valuable tool. I'm going to take you through, this is a busy graph, don't worry about it too much, but I'm going to take you through it. It's a review of different evaluating, these are just different authors evaluating natural mated queens and instrumentally inseminated queens. The natural mates are in blue, the inseminated queens are in yellow. These are the number of queens they evaluated. They're looking at honey production, brood production, longevity. In this group of authors, they said there was equal performance between these two groups. In this group, they said the inseminated queens were higher performing, and that's really based more on selection. And in this one group that is cited often, it says the natural mates are higher performing. But the difference here is in the treatment of queens. The age of insemination, you have a specific time when those queens take a mating flight when they're about a week old. In all these studies, the queens were 5 to 10 days old. They're in that range where the queens normally mate. In the Harbo study, the queens were 2 or 3 weeks. They're past their prime. And we know if queens mate late in their life, or later past their prime, they'll mate with fewer drones, they'll store less sperm. So she's got a disadvantage here. The amount of semen they gave these was from 8 to 12 microliters, which is a kind of a normal dose. We give 8 to 10 microliters of semen. There's about a microliter of semen in each drone. In the Harbo study, he gave 2 doses of 3 microliters, so she's getting quite a bit less. The thought behind that is that the smaller doses will migrate a little bit faster. So she's got, and then the treatment of queens, DR is direct release, or some of these were banked for a few days. Harbo held these queens in a bank for another 2 to 3 weeks. So these queens have not been on comb or been with worker bees for a month to 6 weeks. That's the difference here. If you see a natural mated queen, when she comes back after mating, she's very active, she's running around, the workers are helping to remove her mating sign, the drone parts, and that activity and feeding really contributes toward the sperm migration. So that's important for the queen. So just a bit of a highlight. These queens do perform, they can perform as well as a natural mate in the field. I run them in full-size colonies. I just got tired of people saying, no, they don't do well, but they can, given proper techniques. Okay, we have a lot more. It used to be a way easier to just raise queens and have good quality, but the impact of these new pests and pathogens, and you're having, I think the last number of viruses we've counted was 28 viruses related to having varroa as a vector for parasitic mites. Tropal alaps, another Asian mite, is a little concern. You guys, you don't have hive beetles yet, do you? Okay, well, get ready. It's sorry. It's more a tropical, and where I am, they're not an issue. I live in a cold climate. It's not too bad. They reproduce in the soil. It's too wet and cold for them, so if you're in a colder area, you might be better. We're dealing with these things that are new. Nosema cerani, different kind of brood diseases, pathogens, mostly vectored by varroa is a big problem. You're also dealing with a lot of chemical residues from agriculture, sprays, miticides, different things like this. So these are all just stressors, The nutrition is huge. It's getting more and more difficult to get those bees on good forage. If you can get stressed bees, move them out, get them on good forage, it can just turn that colony over. And that's really important. So if you have malnutrition on top of chemical residues, it's pretty hard for the bees to manage. And that makes them more susceptible to pathogens, diseases. They can tolerate lower levels of parasites, things like that. And you have a big interaction in these. Even with, they've shown that a lot of these chemicals in the environment, there's multiple ones of them, and they have a synergistic reaction, which means they're much more toxic sometimes than each individually. 8 minutes. So this is kind of my take on bee breeding. It's really kind of a balancing act. You got to look at all those kind of factors, genetic diversity, treating the mites, and all these different things. And Rob Page described this really well. He said it's like you have this big balloon, and you're trying to maintain the shape. You push in here, and something odd pops out here. So it's just kind of this balancing act. And you can't really take your eyes off it, because that funny thing's going to happen. I think the game is just to get a good general, uniform population, keep it fit, keep as much diversity in there as you can, so the bees can adapt and change and deal with those different problems. And it's just a balancing act, really. We have some amazing. The whole field of genetics is just zooming. We have a lot of new technical tools. We can tell you how many drones the queen mated with, all kinds of things. I hope to be able in the future, once we perfect some of the marker-assisted selection. Can I just take a little piece of the wing of a drone and, okay, does he have this trait I'm looking for? And then use him or not use him for part of a program. So there's just a lot of really fun stuff going on. But those tools, you also have to take that in the field, because you're selecting for behavioral traits, and those are flexible, dynamic. So you need the field tests to verify that's what you have. And then again, you need to maintain that diversity. If you get too tight with your selection, you're going to kind of miss the overall diversity that creates fitness in a hive. So again, it's that balancing act that really makes it work. Cryopreservation, I mentioned this the other day. This is another tool we're getting closer to. It's not perfected enough that you can have a strong colony, but if we're able to store specialty stocks or breeding stocks in a tank of liquid nitrogen versus having to maintain a population every year, which is very labor intensive, very expensive. That's a valuable tool for research. This is just kind of the process. I went over this yesterday a little bit. It's stored in, there's about 5 microliters of semen in here stored in liquid nitrogen, inseminate the queens, and then you can recover that, which is really exciting. You can conserve, you can reconstruct a species. That's what we've done with the Caucasians in the US. We pretty much lost Caucasian bees, so we went over there, brought in some Caucasian semen, and the only thing I had to cross that with was carniolan, but we could take several generations out of the tank and get that fairly pure over time. You can do selection across time. It's just an amazing tool to really have that ability. This is really common for other industries, cattle, pigs, and there's a big international movement of germplasm on that level. So I think we're finally to the stage where we can do this. And it's much easier to ship a little tube of semen than it is to ship queens, much safer. They are vulnerable to viruses, but still it gives us just more ability, methodology. So again, it's really about the breeding program. I think we have a lot of issues, a lot of problems, but I think the future is really exciting because this whole field, the focus, I see this internationally, the focus now is breeding selection. And yes, the honeybees are a little bit more challenging than most domesticated farm animals we're dealing with, but that kind of makes it fun too. A lot of resources available, so thank you.